All right, you guys, here we are doing our Chapter 10 Means Comparison Significance Test. I am basically in the middle of Section 10.2, starting at the bottom of somewhere in the middle, page like 9, I think is what it is. But it's this bounty versus generic paper towel, quicker picker-upper situation. So we've got some AP Stats students who decided to find out which of the paper towels are better. What they're doing is they're soaking these paper towels with 4 ounces of water. And then they're holding 2 opposite edges of the paper towel and they're counting how many quarters each paper towel can hold until ripping, alternating brands. So here are the results, and it appears just by glancing at the numbers that Bounty can hold a lot more quarters than generic can. And to me, this seems, let's take a step back and think about this for a second. 106 quarters on a paper towel seems like a lot to me, but good for Bounty, whatever. So the first thing, we've got several questions we have to answer here. This is really typical for a like common AP problem 6 type of question where it might take you like 25 minutes to get through a problem because you're doing some sort of a comparison, you're doing a full write-up, and you're answering follow-up questions. So just keep that in mind. That this may be an example of like a 25-minute AP exam question 6 type of free response problem. So display the contribution or distributions using parallel box plots. So I just have a snapshot from the calculator here. Yes, I have everything all written out already. Yes, it might look a little bit overwhelming, but this is just so my handwriting's nice and neat and I can go through really thoroughly all the bullet points and things you need to talk about. But I encourage you to pause the video, type this data into list 1 and this one into list 2, and see if you can get these box plots graphed. This is what you're going to have to do on the AP exam. You might have to sketch these box plots side by side like this. And that's why I labeled my x-axis as so. So how do you tell which one is which in the calculator? You use a little bit of common sense. The Bounty numbers are a lot higher than the generic numbers overall. So that's why I know this one obviously is Bounty and this one is generic. And I also just gave a brief label of my x-axis here just so it's clear. I'm saying that this is like 70-ish because just glancing at the data here for generic, the lowest number I believe is 77 or something close to that. My highest number for Bounty is somewhere around 130, so that's why I labeled that. I think I see a 128. That might be the highest one. And then anyways, I've got a couple outliers here for generic. That's kind of interesting. Remember, mod box plot is the one that showed the outliers. And so in that case, they're probably my 2 very highest ones. I've got 103. I have 2 100s, so maybe one of those dots represents 100 and one of them is 103. Okay, so just a brief x-axis label, and then remember how you're supposed to compare. This is all the way back to Chapter 1. AP Stats is starting to get extremely cumulative, which in my opinion is a really good thing because yes, we have to remember Chapter 1 for the AP exam. Remember that means SOCs, shape, outliers, center, and spread. So you need to mention those things, and remember you need to compare them. So you have to say things like not just the middle is this, the spread is this, the outliers are this. You can't just list a bulleted group of data points about each type of paper towel. You have to compare them. So you should be using words like higher, similar, no outliers, while generic has 2 outliers. Okay, so those are things that you're kind of looking through. You can pause the video, you can copy this down. In your calculator, it's always a good idea to give data to support what you're saying if possible. So yeah, you can come up with the median for Bounty really quickly. This number right here in the box plot, remember your calculator can give you one variable statistics for all of this Bounty data. The median's 116, which is much higher than the generic, which is only 88. IQRs are fairly similar. Again, you can do that in one variable statistics. This is called a very thorough yet concise response that gets full credit because you're mentioning SOCs, you're using context, meaning Bounty and generic and capacity and stuff like that, capability, absorption, whatever. You're talking about the paper towels in your response, and you're using comparative language, higher, similar, while, compared to, so that kind of thing. So Bounty we've got as skewed to the left. We do have a longer tail here on Bounty to the left. The generic distribution is skewed to the right. I'm just saying that because the outliers are here. Otherwise, it looks fairly symmetric. So anyways, it does appear, remember what we're trying to decide here, which paper towel is better. It appears the absorption capability for Bounty is significantly higher than generic. We actually can mathematically test that, so let's do it. Scrolling down, use a significance test to determine whether there is convincing evidence that wet Bounty paper towels can hold more weight, keyword one-sided test, on average than wet generic paper towels can. So, first of all, I know this looks like a lot of stuff. I'm going to go through this defining stuff and stating and condition checking really quickly just because we've been through it a bazillion times, but you're defining what your X for B, I'm using B for Bounty and G for generic. It's the capacity of the paper towels. Yes, it's measured in quarters, so that's kind of weird, but whatever. Make sure you mention what the population is, and we are going to be using the mu's, which are the mean capacity of these paper towels. And remember, for the ho and the ha, the ho, you're always assuming no difference. You can write it like this, or you can even write it in words. But since we have a one-sided test, that means when I do Bounty minus generic, I should get something positive. Yes, you could switch those and make this a less than 0. There's a lot of different ways to write the ho and the ha and still get full credit, so keep that in mind. We've talked about that in class. Here's our introduction sentence. We want to test a claim about a difference in means from 2 different populations. Those 2 populations are referred to as Bounty and generic. Remember that you say that sigma is unknown. The reason why we say that is because we are explaining why we are doing a t-test. And it is a 2-sample t-test for means. Our conditions, there's nothing too crazy about any of that. We have a random sample here, 30 of each type of paper towel. It is nice that the sample sizes are the same, but remember they don't have to be. Independence, there are 2 checks that you're doing, making sure your samples are independent from each other, meaning that the Bounty absorption rate has nothing to do with the generic absorption rate. Those 2 populations are independent and the samples are independent from each other. And then 10% condish for each of those paper towels. Yeah, the sample size is the same, so you can just say each, checking the 10% condition one time, and then make sure that you say, by the way, Mr. or Mrs. AP grader, I'm checking the 10% condition here. For normality, each sample size is equal to 30, so remember the CLT is greater than or equal to 30. We barely made the cutoff. We are safe to use T. You might be wondering, but what about the outliers up here? I thought the fact that when we had outliers, we weren't allowed to use T. And that is a fantastic thought. I'm really proud of you thinking about that if you did. Remember when we're checking box plots and normal probability plots and stuff, when do we do that? That's when we are not told the population distribution itself is normal, and that's also when the CLT doesn't apply. Then we would have to look for outliers or extreme skewness, so this would probably fail that test. However, because we have the CLT applying in this case, both of our sample sizes are 30. That means that these outliers don't make enough of a difference and that we are still safe to use our T distribution. So remember, T is robust, and our T calculations are still going to be relatively accurate despite these outliers. So just keep that in mind, that we passed the CLT, and so therefore those outliers aren't as significant. That should make sense. If our sample size is 5, then one of those being an outlier is going to make a huge deal. If our sample size is big enough, and big enough is defined by the CLT as bigger than or equal to 30, then those outliers don't make as much of an impact. So just make sure that you've got each sample size is equal to 30, CLT applies, that means it's safe to use T. Even though we have outliers in the distribution above, that's not what we're checking for in this case because our sample size is not too small, defined by greater than or equal to 30. Anyways. So you've got the data typed into your calculator, and here are all the statistics. You can do 2 variable statistics to have it do list 1 and list 2 all at once. So just keep in mind you probably put the bounty into list 1, so this is technically your X bar 1 in the calculator, and then you probably put the generic into list 2. So just make sure that you're using the right numbers in the right spot. The alpha is 0.05 since none is given. And then remember the degrees of freedom from the calculator. You need to be able to get that from the calculator because this is a much more accurate degrees of freedom than using the conservative, which is the smaller of the 2 sample sizes minus 1. The calculator does a much more accurate calculation of degrees of freedom based on the sample sizes, standard deviation, all that stuff. And so what we're going to use here for our degrees of freedom is 57.84. Remember how to do that is to get this, is to run the actual test in your calculator. So this is a 2-sample t test. And then it will spit out a bunch of stuff, including the test statistic, including the p-value, and the degrees of freedom is one of those things. So yeah, it kind of gives you all the answers, but remember you need to show all the work too. So that's a good way to just double check your work and make sure you're doing all your calculations correct. Anyway, so remember our test statistic is a t in this case because we don't know our sample standard deviation. Sigma is unknown. We don't know our population standard deviation. That's why we're using a t for our test statistic as opposed to a z. And then our statistic is the difference between our two sample means, minus the parameter is what we're taking from the hoe, which is just assuming no difference. That's equals 0. And then this is the formula from our formula sheet. Your two different sample standard deviation squared divide by n's. So the two different n's, in this case, they're both 30. So plug all the numbers in, and that gives us a test statistic. So the t is 17.644. Remember, a t distribution is a little bit different from a normal distribution, but the test statistic kind of works like a z-score, kind of, but it's a t. And so think about going 17.6 standard deviations to the right of the mean. You shouldn't even need to type this in your calculator, but if you do, you're doing TCDF in the calculator. 17.644 to the right forever would be positive infinity. And then with this degrees of freedom, gives you a p-value basically 0. Remember that your calculator might be so exact that it gives you a number in scientific notation like 1.29 times 10 to the negative whatever. That is basically 0. So just keep that in mind, that if your calculator gives you scientific notation, just know that that is approximately 0. Again, our p-value is less than alpha. It's about 0, which is definitely less than 0.05, and we're using 0.05 because no alpha level was given in the question. And when the p is too low, you reject the hoe. So we reject the null in favor of the alternate. And then remember, when you reject and you favor the alternate, that's when you restate what the alternate is. And the alternate says up here that bounty is better than generic. So we're saying that in terms of weight capacity in quarters, being as specific as you can in your conclusion, going back to getting some context points, make sure you talk about bounty, generic, weight capacity, quarters, all that kind of stuff. Okay, so the last part of this question, again, I know I'm writing a lot of stuff, just pause the video if you need to and copy stuff down, but when you're interpreting the p-value, remember this is different from concluding. Concluding we did up here. Interpreting the p-value, this is your template. We've talked about this in class before, but plugging in the context and stuff to this template would mean that if the mean capacity for bounty and generic paper towels is the same, remember this is the null in context, that's what this sentence is. Assuming the two are the same, there is about a 0%, that's your p-value, whatever the p-value is, that's your percent chance of observing a sample mean difference. So remember, we took two different sample means and subtracted them. So that's observing a sample mean difference greater than or equal to the one we observe. So this was our sample mean difference. And so if we had our t distribution, we drew our line at 29.467 and shaded to the right. That's the shaded area is the probability of getting a sample mean difference at 29.467 or greater. Okay, and it's or greater because there is this was a one-sided test. Remember, we would double that p-value if it was a two-sided test. The p-value is the probability of getting a sample like ours or more extreme just by chance. And so since that probability of getting a sample mean difference is so low, that's so unlikely, that means we do have evidence that bounty is better than generic. Thanks for watching, you guys. Bring your questions to class. Hopefully all that stuff made sense, but we are almost done with videos. You guys are doing an awesome job. Have a great night. I'll see you tomorrow.